Hello, this is one of the State of ZX meeting talks, and I'm discussing measurement-based quantum computing and the ZX calculus. My name is Miriam Backens, and my pronouns are they, them. So you're probably familiar with the quantum circuit model, where we represent quantum computations by preparing states in the computational basis, measuring in the computational basis at the end, and really putting all the main parts of our computation into the unitary part, which we decompose in terms of individual gates. That's a model that arises from the idea of classical logic circuits. The one-way model of measurement-based quantum computing, on the other hand, is an intrinsically quantum model where we start by preparing an entangled graph state, and then the computation proceeds by successive adaptive single-qubit measurements on this state. And so we're making use of the fact that our measurements change the state that's being measured. So this is really something that can only work in the quantum world. One of the important things about this model is that because of the way that individual measurements are non-deterministic, we have to do the measurements in a successive way so we can adapt later measurements to compensate for having seen an undesired outcome earlier and make the computation as a whole deterministic, even though individual measurements are not. By the way, I don't expect you to understand the sequence of commands here if you're not already familiar with what that means. It's just there as an example. So moving on to other ways of representing these computations, the ZX calculus can be used to write down quantum circuits. If the circuit is already expressed in the controlled knot and single qubit gate set, that translation is particularly straightforward. And we can also use the ZX calculus to express measurement-based computations. But in that case, what we're writing down is actually a little bit different to what's kind of the standard measurement calculus notation. So in the ZX calculus, we're drawing the graph state. So that's really kind of a visual representation of this graph. I'm going to talk a little bit more about what a graph state is in just a moment. Whereas here in the measurement calculus, we've just kind of got a sequence of commands that's meant to prepare the graph state. So that really doesn't show us how the graph looks. On the other hand, here we've got, as I've just said, a sequence of commands. So that really gives us some kind of time ordering. And that time ordering is not there in the ZX diagram. So we're just showing the graph. We're showing what kind of measurements we want to do. We're also not showing the Pauli corrections, which we can explicitly write down here in the measurement calculus. But in a few slides' time, I'll explain to you why that's actually a valid thing to do, why we can recover that information, even though it's not explicitly there in the ZX diagram. But first, let's move on to looking at graph states in more detail, just in case you're not familiar with them already. So a graph state is based on a mathematical graph. So for each vertex in the graph, we prepare a qubit in the state plus. So in ZX calculus, that looks like this. And then for each edge in the graph, we apply a controlled Z gate to the corresponding qubits. And in order to keep our diagrams a little bit less cluttered, we've introduced the convention that we draw these edges with Hadamard gates on them as just a blue dashed edge. Because it means we can make the diagram smaller without losing the ability to read what's going on in that diagram. So why do we like graph states? They have a property called the stabilizer property, which means that they're eigenstates of tensor products of Pauli operators. And we can prove that in the ZX calculus by introducing two Pauli x's on one of the wires, which of course two Pauli x's cancel each other out. And then we can take one of those and we can push it, we can copy it through that green spider down here. And remember these blue dashed edges, they actually have a Hadamard gate on it, so the color changes. And what we end up with is Pauli z's on all the neighboring vertices of our original one. So in this way, we can see that our graph state is indeed an eigenstate of this particular tensor product of Pauli's, and there are others as well. And it's these tensor products of Pauli's that stabilize the graph state that we use to correct measurement outcomes that we didn't like. So to look at things in a little bit more detail, so the kinds of ZX diagrams that represent a one-way model computation, they consist of the graph state that we've just talked about. We've then got an extra input wire on some of the vertices. So that means we need to be a little bit careful with the stabilizers. If we try and copy a red pie through a spider that has an input wire, then things go a bit wrong. But in general, broadly, we can still do a lot of the same things anyway. And then finally, the important thing, it's a measurement-based model, so we need to represent the measurement effects for our vertices. And in this model, we've got 6 different kinds of measurement effects. We can measure in the Pauli basis for each eigenbasis of each of the Paulis. And we've also got 3 different types of so-called planar measurements. So these have a continuously varying parameter in them and represent these families of measurements that we can do. And then in order to find out whether we can do this measurement-based computation in an overall deterministic way, we're looking for a correction strategy, which is called a flow. So there's all sorts of different types of flow, but what they all have in common is that they consist of a partial order on the graph vertices. So that tells us something about which order we need to do the measurements in, and also a stabilizer for each of the measurements, which is the stabilizer that we're using to correct that measurement. And of course, these 2 things, the partial order and the stabilizers, as well as the underlying MBQC form diagram, they have to satisfy certain compatibility conditions for there to really be a flow and this to all work out. So the good thing is that there are polynomial time algorithms that allow us to find flows given an MBQC form diagram or determine that no flow of the type we're looking for exists. And so if you give me such a diagram, I can always tell you whether that supports a deterministic measurement-based computation. So now that we know that flow is important, if you give me a diagram that does have flow, sometimes I might want to change that diagram, for example, to make it smaller and simpler. But I'll want to preserve this property of having flows so that it can still run a deterministic measurement-based computation. And so for that, we need flow-preserving rewrite rules. And 2 of the kind of first ones of those that people came up with are the so-called local complementation rule, which if you've ever worked with graph states, you're probably familiar with. And also a rule that allows us to delete or insert Z measured vertices into our MBQC form diagram. And that's really an interesting aspect of these flow-preserving rewriting rules. We're used to our ZX equations going in both directions. They're equations. They don't actually have a directionality to it. But if we want to know whether something preserves flow, we actually have to prove that separately for both directions. In some cases, it's kind of implicit. The local complementation is self-inverse. If we do it 4 times, we go back to where we started. So there it suffices to prove it for one direction. But for Z deletion and insertion, we do really have to prove it separately for both directions. One of the really nice things about these 2 rules together is that they're complete for stabilizer ZX diagrams with flow. So stabilizer ZX diagrams are those where all the phase angles are integer multiples of pi by 2. It's really interesting to have just 2 rules be complete for this fragment. If we look at the general stabilizer fragment of the ZX calculus, we've got something on the order of just under 10 rules, I believe. And most of those are in fact proved to be necessary. Whereas in this flow-preserving case, we've only got a much smaller set of rules. The rules themselves are more complicated because they need to preserve the MBQC form and, of course, the flow. But yeah, still, there's only 2 of them, which is very neat. We've also got a number of other rules that people have come up with that allow us to also handle measurements that have these continuously varying phase angles, the planar measurements. But the question of a complete set of flow-preserving rules, that's something that we're, for the general case, is something that we're still working on. There's a lot of applications to this combination of measurement-based quantum computing and the ZX calculus. So these flow-preserving rules that we just talked about, they can be used for optimization by expressing circuits as a ZX diagram and then treating that ZX diagram as an MBQC form diagram. We can use that to, for example, minimize the number of T-gates or other non-Clifford gates. This has also been used to reduce the number of 2-qubit gates in a circuit. And we can also use it to look at other aspects of a computation, for example, fusion networks for graph states. So graph states are in the photonic quantum computing, we can create kind of small graph states, but not very big ones. And so these small graph states need to be composed into bigger ones in some way. And again, that's a non-deterministic process. And so it's important to work out which of these, what's the kind of most efficient way with the the least non-determinism involved in it, that will get us to the goal. There's another application of this combination, which is in blind quantum computing. So that allows a client to securely delegate a quantum computation to one or more servers in the cloud, with the client themselves needing only very limited or no quantum computing capability at all. And sort of standard protocols are based on these universal resource graph states that allow you to do any computation. But of course, in general, if you use such a universal state, that will actually waste quite a lot of the qubits, which aren't going to be directly involved in your computation. And so there is a more resource efficient protocol which uses these kind of ZX optimization techniques while preserving the security properties. And then looking more at the ZX calculus itself, it was recently shown that translating an arbitrary ZX calculus diagram into a quantum circuit, even if we know it's unitary, is something that's number p hard. But if we've got a ZX diagram with flow, we know that we can translate that into a circuit in polynomial time. And it is in fact very easy to take a completely generic ZX diagram and bring it into this MBQC form so that we can decide whether or not it has flow. And so this circuit extraction procedure for ZX diagrams with flow is really the most general algorithm that we have, efficient algorithm for taking a ZX diagram and turning it into a quantum circuit. So to summarize, I've talked to you about two different models of quantum computation: the circuit model that is taught in all introductory courses to quantum computing, and the one-way model, which is something much more intrinsically quantum. And I've talked about how we can use the ZX calculus to represent both of those models and also translate between them. And I've given you several applications of using the ZX calculus and these two different models in this way. There are loads of topics I didn't get around to discussing in this talk. So measurement-based quantum computing is actually something broader than just the one-way model. So there are other computation schemes that involve measurements, from something like gate teleportation or magic state injection, all the way to other models that use kind of measurements for almost everything, such as the Pauli-based computation model, or the kind of fusion-based model in surface codes. I've also only talked about the one-way model on qubits with graph states. It's possible to instead look at one-way computation on hypergraph states, which is something that, rather than expressing it in the ZX calculus, we would use the ZH calculus for. And there's been a little bit of research on that, but not all that much yet. There's also some work on measurement-based quantum computation using qubits instead of qubits. And yes, indeed, probably other topics that I'm forgetting. So yeah, let me wrap up here. I'm already a bit over time. Thank you very much.